Good morning, everyone. I'd like to welcome you to a new lecture of data warehousing and data mining. Professor Balke will not be joining us today. He's out there in Bonn, even though there are strikes in the Bahn, so I'm not sure how he's going to get there, but let's hope he does. So today it's just going to be us together, and we're going to be talking about indices. So just a quick recap of what we did last lecture, because it's actually tied up to what we're going to do today. Last lecture we talked about the different models that we use. So we had a logical model, and at that core we used the cubes because we had a multi-dimensional data and we needed to handle that. And as soon as you decided on your primary citizenship in the data warehouse, you created a cube, and then you started identifying the dimensions that describe this cube. And for each dimension there were different hierarchies and different classification levels, and we saw how these classification levels can actually sustain different evolutions. Then we hopped on into the physical level, and for that we had different models that we could use, like ROLAB and MOLAB. These were the most interesting ones for us. In the MOLAB, basically, we looked at how you can store that on the disk, and with that we used arrays. And we saw how with arrays you basically had to linearize, and usually you had to only choose one dimension. So last time we had one example where we basically restricted ourselves to two dimensions, which was the product and the time dimension. And basically at the end, what you do is you linearize according to one dimension. And what happens is on the disk you read sequentially, which is good, depending on what kind of query you get. So if we linearize according to the time dimension, and we get a query about January and February, this was easy to read from the disk because everything is in sequential order. So that was good. If on the same linearization that you did, you get a query about the products that were sold, different products in January, that would have been difficult because the data is not linearized according to the product dimension. That meant that you had to hop in different disks on your platters, right? So that was one of the cons of using arrays. Then we hopped onto the relational model, and there we started looking at the different schemas that we had. So we had star and snowflake schema and starflake schemas and galaxies and all of these fascinating names, right? And behind all that we had fact tables, and we had, with each fact table you had the measures and the foreign keys, and the foreign keys basically then pointed at the different dimensions, and the dimensions could have had different classification levels, and so on and so forth. So this is what we did last time, and this is how you actually store the data. But the problem is now is that this data, all the data that you have is scattered. So as you've seen, when we used the multidimensional model and the linearization, it worked in one dimension, in the other dimension, not very well. Same thing if you work with fact tables on dimensions and you get a query. You'll have to go to the fact table, and then you have to follow all the foreign keys and do the joins across the dimensions. So the problem is now, how can you access the data in a very efficient way? Remember, your data warehouse is huge. We're talking about terabytes, we're talking about petabytes. And you need to find a clever way to access these scattered data on disk and quickly. And this is where what leads us to today's topics, which is indexes. Done. So today we'll be talking about how we can access the data cleverly. We'll be looking at tree-based indexes, and if you've done either of relational database 1 or 2, anyone who's done any of these lectures? Anyone who did not? Some people are still sleeping. Maybe like me as well. Cool. Well, if you didn't do it, we're going to take a look at it today, right? And then, very interesting for those who did take RDB, or maybe the tree-based indexes will be different, we're going to look at something very specific for data warehousing. So bitmap indexes were developed for data warehousing, so they were specifically designed for multidimensional data. And we'll take a look at both of these types of indexes. Cool. So why indexes? So I've gave this introduction, and maybe right now you're a bit convinced why we need indices, but let's look at an example. So consider we have a 100 gigabyte table, right? And this is actually a very conservative number. So as we've said, data warehouses, they're petabytes. So 100 gigabyte is actually very small, right? And we have a 100 megabyte reading speed. The amount of time that you need to do a full table scan would amount to 17 minutes. Now you're sitting there and telling us, well, you told us in the first lecture data warehousing is, well, a database support system, so 17 minutes, that's fine, right? I mean, we could wait. It's not like these OLTP queries where we need the answers right away, but we can wait. The manager up there can wait, right? Well, you're right, except this is 100 gigabyte. If we go to petabytes and terabytes, you can imagine that this number will also grow substantially. And this will not cut the slack with it, right? So another problem beside the time is actually you don't have anything to say, okay, I'm taking a lot of time because I'm actually bringing huge amounts of data at the end. So the selectivity actually is very small. So it makes the whole 17 minutes for the 100 gigabyte rather not really worth it. So as an example, let's assume I have my data warehouse is about products, and I'm looking for the Bosch S500. So I'm querying this washing machine, and I want to know how many Bosch S500s were sold in Germany and last month. So here there's a restriction about the product, the location, and as well the time dimension, right? And assuming that the cardinalities for the different dimensions are you have 30 locations, you have 10,000 products, and only the last 2 years in the data warehouse. So the selectivity that comes out of the query that you just posed, the number of Bosch S500s that were sold specifically in Germany in last month is basically 1 of the 30 locations, 1 from the 10,000 products that you sell, and only 1 month, so last month, from the last 2 years that you've been saving. And this is exactly the number of tuples that will answer the query that you posed. So you basically have to read 100 gigabytes to get only 1.4 kilobytes. And to get this 1.4 kilobytes, you take 17 minutes. Not very impressive, is it? So the idea is, if I'm only getting 1.4 kilobyte at the end, and I was only working with 100 gigabytes, we definitely need to find a solution. So data is very scattered on the hard disk, and we need somehow to devise some algorithm or mechanism to cleverly sit on top of the disk to allow us clever access to the data. So what we did in the slide before, we had here the Bosch washing machine and the time dimension here. And this is the 100 gigabyte data that we had. And what we did is, this here is exactly the data that we want to get, the 1.4 kilobyte data that we're searching for. So it's kind of like a needle in a haystack. And what we did is, we scanned all of this data. And all of this is wasted because none of them is relevant to the query I'm looking for. So you scan all of this, to at the end get this piece of information over here. Bad. What you can do a primary index. So you basically index one of the dimensions and you index the primary keys. So if you do that on the time dimension, this gets way better. So now you know exactly at which time you need to look at, so last month, and then you just have to scan then the 10,000 products that you have in order to finally get to this one product, the Bosch S500, and then you get the data that you want, the data that answers your query. Better. You can also do secondary indices. So you can build 2 secondary indices, on the 2 dimensions. So now you have an index on the time dimension, a secondary index on the product dimension, and basically then you read everything for the Bosch S500, everything for last month, and then you get the intersection, so basically what is relevant for your query. But all of these methods up until now, you still need to scan parts of your data in order to get the 1.4 kilobyte. What we want to do, or what we are going to come very close to today, is the perfect solution, which is you create a query, hop into the data warehouse, you know exactly where to go, and you directly get that piece of information that you need. This is the best solution. We don't reach it, but we're very close to it. Yeah? And this is what we're going to see today. Cool. So when we first started thinking about tree-based indexes, well, the very first thing that came into mind at the very beginning was, well, back in the early 70s, so B-trees were invented by Rudolf Bayer. And in 1972, basically back then the main memory was a very scarce resource, right? So you wanted to make sure that if you're going to get data into the main memory, you have to do it in an efficient way, you have to do it in a clever way. So what they thought, well, okay, we need to build some kind of a data structure that sorts the data. And once you are able to sort the data, you have a data structure that sorts the data that is underlying in the databases or on the disks, then you can actually then start thinking, well, these blocks might contain my query answer, so I go look into them, and some of these blocks, well, they will never hold the answers to the query that I need. So as soon as you start sorting the data, you can realize then, okay, I can skip these, right? These probably will have the answer that I'm looking for. And so what they did is they started sorting the data, and they did that by using nodes. So a tree basically have the following structure. You have a key value, and the key value might be the value that is stored on the disk. So if we're talking about numbers, so this is easy to do. If we're talking about strings or vectors or something more complicated, this key value might be just a criteria. So it might be a primary key, something that identify the element that the key node is pointing to on disk. And then you have so-called node pointers. So the pointer on the left is all the elements, all the key values that are smaller than the key value in the middle. So this is here 6. This would be a 5 up until negative infinity or something. And everything on the right is bigger than 6. So all the children on the right are bigger, or the children on the left are smaller than the parent. And then you have a data pointer over here, and the data pointer takes you exactly to the hard disk where this key value exists. So it takes you to the location. So as soon as you find the key value you're looking for, you hop into the data pointer, and it takes you to where that value is on disk. So let's look at an example here. Here we have, this might be like the boot, and you have values 2, 6, and 7. You see everything here on the left side is smaller than 2. So we have 1. Everything on the left side of 2 is bigger, so 3, 4, until 5. At the same time, they are smaller than 6, so they are on the left side of 6, and so on and so forth. The nice thing about B-trees is the so-called bushiness factor. So B-trees are a generalization of binary trees. So binary trees are exactly like the B-trees, except that they are limited to having 2 children. So every node have only 2 childs. So here you can see that the levels are, the width is higher than 2. And this is the bushiness factor. And this is actually nice, because then the cost of traversing the tree then is always related what? It's related to the height of the tree, right? Because whenever you're looking to a tree, so now I need to get to node 9, So what do I do when I traverse the tree? Well, I go here, and then I start looking. 2, 9 is bigger than 2. 6, 9 is still bigger than 2. 9 is still bigger than 6. 7, 9 is bigger than 7. So I hop to the right pointer, and then I start traversing until I found the 9. And at the data pointer, it takes me here. So here, to get the 9, I had to traverse 2 levels of the tree. If I was lucky, maybe I would have chosen the 6. So I go inside. I only have 1 level, and I get the disk. So the cost of getting the data at the end is directly related to the height of the tree. Thinking of a binary tree, where you only have 2 childs, then you have the height of the tree gets bigger. With the B structure, because the degrees of the nodes here, which is basically the number of childs, it's relatively small compared to the overall numbers that you have, all the number of data items that you have in the cost. This then basically becomes a logarithmic base, and so the cost at the end is logarithmic, right? Something also very clever about B trees, which makes them very popular. I mean, they're still used up until today. They've been invented back in the 70s, but up until today in databases, and you will find B trees or different versions of B trees, B plus, B stars, so they're very powerful. And one of the reasons why they're so powerful is the efficiency they achieve by the mapping that they do between the nodes and the disk blocks. So the idea is, how many children do you think you would put inside a node? Do you determine that pre-hand and say, I'm always going to put 4 or 2? What do you think?
No, you do as much children as they can fit into one block.
Exactly. Yes. And why is that?
Because you have to read the whole block always. You cannot read only half a block, and if you have to read all of it, so you should fill it and don't waste space.
Yeah, that's exactly the perfect answer. So if you choose number of children that are smaller than 1 block, well, it's going to work. But then you're wasting memory in the disk, so not very efficient. If you put children that are extending more than 1 disk block, so you end up then here with an element, for instance 5, and then it's exceeding the 1 block. You don't know, is it in the first block or in the second block, so you end up reading 2 blocks. Not good. So the basic idea is you fit here as much children that would correspond to having their data residing in 1 disk block. So you usually know the amount, what are the sizes of the data, and then you try to fix it to fit it into 1 block. And of course, if you have a data item that is bigger than 1 disk block, well then you can't do anything about it, so you basically put it in 1 disk block, and then there's sequential, so the disk blocks, then you have sequential pointers, and then you still do the sequential reading in the disk. So this is still better than having them in completely far away disk blocks, because then the head is basically on the platter and it just reads sequentially in the disk block. Good. So the idea is now you've seen what a B tree is, which was basically one of the first trees that were designed and implemented, but we're actually talking here about data warehousing. And data warehousing, we're talking about multi-dimensional data. So how does the B tree now fits into our context? Because what I've been telling you now is you have numbers like 6, and everything that is smaller than a 6 goes on the left side. Everything that is bigger goes on the right side. And then you can basically traverse throughout the tree and find what you're looking for. But that is not how our data looks like, does it? I mean, we have more than 1 dimension. This is clearly 1 dimension, isn't it? So what do I do now? I have the Bosch S500, all the washing machines. I have the locations of different branches. I have the time dimension. What do? Do I linearize only on the product dimension and say all the products that starts with an A are smaller than the Bosch, and everything that is big on C is then on the left side? Do I only make it on the time dimension? Our data is usually multi-dimensional. That means it's projected in a data space. What do you do if there's a point here and a point here? Which is bigger and in which dimension exactly? So it doesn't really scale, does it? So the question is, that the people started thinking about was, okay, we have the B trees, but can we do something with them? Can we extend them to multidimensional data? And that took some time because, as you can imagine, multidimensional data, you're hopping into n-dimensional space, and these lines, left and right, doesn't cut it at all. It doesn't work. And the idea came to them when they started looking at geometrical models. So they said, okay, we have our m-dimensional data space, and we have points in space, right? And they started looking, okay, we're in the space, so why don't we start partitioning the space? Because usually data that you have in the real world, there is this notion of closeness of the data, right? You have different dimensions, and usually your data space will be not dense, in the sense that you won't, all the data in your data warehouse won't fill your entire data space, because that would mean that for every dimension that you have a data point that basically gets all the combinations of all the different dimensions, but that will not happen. So let's think about the washing machine example. You will have, the best washing machine will be, I don't know, takes 10 kilograms clothes, very efficient on energy consumption and whatnot, and it's going to be very expensive. So that's maybe up here, very good one. And then you have the cheap one, 1 kilogram washing machine, uses, I don't know, normal soap, not liquid, doesn't have softener, very bad in energy efficiency. That would be cheap. You will not find a washing machine with the bad specification being expensive. That will not happen. But rather, you're going to start finding clusters of data. Some washing machines that share the same characteristics, that have intermediate qualifications, they're also going to have an intermediate price range. Others with higher specification, they're going to be up here. So not all the combinations of the different dimensions are going to work. And so this idea of closeness, where data points that have the same characteristics in different dimensions are close in space. And what we want to do now is we want to translate this closeness into the space to the closeness on the disks, right? So what they started thinking about was, well, why don't we look at the space in terms of a geometrical region and start exploiting this kind of data closeness or data locality, and say, okay, in the data I have this cluster of data here. They seem to be close to each other. They seem to be related. So if I get a query about the expensive washing machines, they seem to have a special characteristic. So these seem to be close to each other. So these should be clustered together. These should be saved together. And then I have these over here. They seem local. They seem to be in the same neighborhood. And maybe those over here. And then you have 1, 2, 3. You create some 3 clusters. So basically you take the points and you bound them with a geometrical construction, a geometrical region. So what we want to do now is we want to transfer from the B trees, from having to look at individual points where we had the 6, the 2, and what is bigger and what is smaller. And now we want to transfer to, well, a cluster or a geometrical region, whatever that looks like, a sphere, a cube, that encapsulates different points. And this then allows you to basically abstract from the different individual points And now you can compare the points to each other with the respect for the location in the region. Good. So now you can have now clusters of points, and as we will see later, you can also have different clusters inside that contain each other so they can overlap. So you start building clusters of points, and you can get some structure later on. So this was the basic idea from transferring from individual points to regions and spaces and encapsulating the points within a geometrical structure. But how do you actually then create the tree structure? So there are different criteria to take into consideration. So first thing, we're talking about cluster construction. So how does that cluster looks like? Well, you have two options. Either you fragment the space completely. So that would mean something like having a grid structure. So you have all the points that were here as well, if my memory serves me right. And then what you do is you basically construct something like a grid. So you completely fragment the space, and then each point is in a cell, and is described by this cell. So individual points. Or what you do is what I've been talking about is, well, basically you describe the data by locally grouping them together. So you start doing clusters of points, and you abstract from the individual points and go a higher level up so that you can start describing or comparing the points relative to each other. So with such tree structures, what we do is we go into some kind of into a Euclidean space. Of course, we're talking about multidimensional data. But just for simplification now, we're going to be looking at two-dimensional. However, everything that I'm talking about, it can still go up higher into more dimensions. But the good thing about having it in a Euclidean space, the most important thing is that you have to have these dimensions, they have to be ordered. Which means if you have all the Bosches, then, and the products are strings, you can then have a lexic order. So okay, you can say then, okay, the Bosch is here. What other types of washing machines there are? Siemens are here. I don't know if they do washing machines or not. So you order them with the alphabetical order. And if there's numbers, then you enforce number order. And then you can actually look at the coordinates of the different. So this could be the price, for instance. This is $100 up to $1,000. And then you can say, this is Siemens, and this is another Siemens, but it's more expensive. So what you do now, by going into the Euclidean space, you can start comparing the objects by their distance. So if you find a Bosch here as well, so the distance between them in space determines how similar they are. And this basically also plays an important role when we're thinking about clusters, similarity of objects that are together. Objects that are similar will tend to be clustered together. Objects that are dissimilar, they're going to be in different points in the data region. And if you get a query, then you're querying similar objects maybe, and then you want the cluster, right? So this is grouping the data locally. Another thing to keep into the mind is, well, you're going to create clusters. Do you want them overlapping or do you want them disjoint? And we're going to see that overlapping, though it might not be very good for us, because what overlapping means is, well, you will basically have some point within two clusters. And when that happens, when you have built a tree that is actually mapping to this cluster, to this data space, this means that this object will be in two places in the tree. So this is R1 and R2, and you have the tree, you have the root, and you have R1, and you have R2 here, for instance, and then A, B, and this is X, and X is basically in the overlapping region. So you will have the child A and X and B maybe. And when your query comes with X, you go inside here, and you don't know, should I go into R1 or R2? So you end up looking in both branches. And we're going to go into details into that in the next few slides. But overlapping usually is not good because then you don't know exactly which cluster it's in. But unfortunately, sometimes it's unavoidable. But it is something that you have to decide at the beginning. Another thing is, well, the tree, should it be balanced or unbalanced? Balanced means the clusters usually will have the same number of children, so they are of the same size. Or unbalanced meaning, well, something like the left deep tree, so what we use for query optimization. Balanced will always be probably better. And why is that?
Because the conversation of the tree is more balanced actually, because the search parts are equal distance.
Mm-hmm, exactly. So then, as soon as you get these unbalanced trees, if you go into the search, you have to go deep into the tree. If you have something like the B tree, which is bushy, then the levels that you need to traverse are smaller, and then your cost of searching into the tree decreases. So balanced trees are always advisable. And then we still have to look at, well, what do we do with the actual objects? Do we store it in the leaves of the tree and the internal nodes? I mean, this is doable if the data that you have is rather small, so you can do that. So this was the example with the B tree at the beginning. Or you could only keep the data at the leaves. That is if they are big. Or you can only keep some criteria, so some kind of like a primary key that tells you, okay, identifies the object, and then using the primary key you go and get the data from the disk. So it's basically depending on the data that you're storing. And the last thing, which is basically one of the core things that we need for the multidimensional tree, is the geometry, these geometrical regions or structures that are going to enclose the individual data points. And these are different depending on the types of trees that you use. So you could use a hypersphere, and this is very prevalent for M trees. So if you're talking about 2 dimensions, then it's a circle, and then as you go up higher in the dimension, then it becomes a hypersphere. And there are hypercubes. These are prevalent in R trees, and this is what we're going to be doing today. It starts off with an array, higher up the dimension, and it becomes a hypercube. Very good. So R trees were the first multi-dimensional trees that were thought of, and they were thought of by Goodman in 1984. Well, and back then, data warehouses were still not the motivation behind it. So basically, the idea came from having to deal with multimedia and having to work with geographical information systems. And they needed then some structure to hold these multidimensional data. So it became an extension of the classical B trees. And it was good up to 10 dimensions. But as soon as you go up higher than 10 dimensions, the trees start to degenerate. And to degenerate means that some parts of the trees will have more children, so it becomes unbalanced. And as soon as that happens, and it gets degenerating, then you might end up with a linear scan, and then the index then is useless. Then you might as well would have completely ignored the index and just hopped directly into the disks. More scalable versions of the R trees are R plus trees, R star, and X trees. And these actually go up to 20 dimension in actually the worst case scenario when the data is uniform. So when your data space is dense, not sparse, but like we said. So you have all the different combinations for all the different dimensions, and usually in real life data that does not happen. However, assuming that you do have uniform distributed data, then as soon as you reach 20 dimension, we always say this is the dimensionality curve, and it's kind of like the magical frontier. As soon as you hit it, things start to get tricky, and the structures that we have do not scale to hold such large dimensions. Good. So our trees are basically trees that are dynamic, which means you can do the normal insert, update, and delete operations. You have two types of data structures. You have data pages, which are basically leaves. And the leaf nodes, they store two things: clustered point data and data objects. Clustered point data is basically the coordinates of that geometrical structure that is encompassing the individual points, so which cluster this point belongs to, and the data objects, what points are within this cluster. And the directory pages, these are basically the internal nodes that are used for navigation. So these are the nodes that are in the middle of the tree that are used to navigate to the leaf nodes over here. And in the R trees, data is only stored at the data pages, so only stored at the leaf nodes. Directory pages, they only use for routing within the tree. And lastly, in terms of the geometry, what is used in the R trees, we use so-called minimum bounding rectangles. So we use rectangles to bound the points. And the very interesting, or the key word here is minimum. And this is very important. So if we have points in space, what we try to do is, well, we're going to draw a cluster, we're going to try to put them together, and what you do is, you don't say this is my cluster, this is a bad grouping of the data points. And why is that? Well, because it's actually your data points are only here. If you do something like that, if you say this is the cluster that contains these data points, what happens later is, if you want to search within the tree, your search query comes, and you want to intersect the coordinates with the cluster that you have. And let's say it actually exists here, or it should exist here, right? But it's not saved in a data warehouse, it doesn't exist in your tree. You're still searching for it. So when you first start looking at the tree and the different clusters that you have, you will find a cluster that looks like this. It's big, which means, well, it seems like the search query might be there. So what you do, you start traversing the tree. Only at the end, you reach the leaf pages, and you find out, oops, it wasn't there. And this is because you have a lot of dead space here. So this bounding rectangle was too big. It's kind of like a delusion. It's kind of like a lie. And instead of finding out from the beginning that this search query does not exist in the tree, you thought that it might exist because the cluster had space for it. And trees or indexes, the most powerful thing that they can offer is pruning effect, which is from the very beginning you can find out whether it is sensible to traverse the tree or not. If you from the very beginning know it's not in the data warehouse, not on the disk, then you can prune the branch. So if we had done something more clever and basically said, well, this is the minimum bounding rectangle, then the search query, when it comes here and it tries to intersect with the tree, with the clusters in the space, the coordinates are not there. So from the beginning you say, this is not in the data warehouse, this is not stored on the disks, and you don't need to traverse the tree. Or maybe this is only one branch of the tree, so you basically prune it and you're done with that. So the geometry, it's very important to have minimum bounding rectangles, and that is to minimize these dead spaces, which then leads you to traverse more and more. You start looking in the tree because you think you might find the answer to your query when it's not there. So you always have to try and avoid that as much as possible. So here is an example, because now I've been talking a lot also in space. So let's get our hands on deck and see what does an R tree looks like, the tree, and how it actually corresponds and maps to points in space. So basically you start off, of course, with the root. And the root is basically the minimum bounding rectangle that contains everything in your space. Now notice here, of course, as you can see, there is dead space that I was telling you about before. However, this is not there. So this should actually be here. But this is just for you to be able to see the different lines, because if they're overlapping, well, you can't really say. So this dead space does not exist. This is just for us to be able to see more clearly, right? So the root is basically your entire data space. And then you have the second level are the different clusters. So here we have 3 clusters, R1, R3, and R2. And as you traverse down the tree, you have the different clusters, different minimum bounding rectangles that are holding the individual data points. And remember, each internal root, what does it have? It basically tells you the coordinates of the bounding rectangle, so you know its location in space, and the individual points that are inside, which is basically the pointers to the children. But you know the coordinates of the rectangle. And now, when you basically get a search query, what you do is you take it to the root and you see, is there any intersection between the search query and the root? And if the search is here, looks like it might be there, you go second level, you check in R1, R2, and R3, and you will find that they do not exist in either of the 3. So you don't go down. You don't go here or here or here. Good. If you recall, a few slides ago, we talked about, well, the multidimensional trees, and then we started looking and said, okay, at the very beginning, you need to take into consideration some of the characteristics of the tree. So conforming to these characteristics that we were talking about, how does the R tree fit into that scope? Well, first of all, in terms of the clustering, the R tree has a local grouping, so it doesn't fragment the space, it doesn't look at each individual points, but rather it has the minimum bounding rectangles, and these rectangles basically then groups the data points in space. So they conform to the local grouping, and they try to maintain the closeness of the data points in space. Second, they allow overlapping of the clusters, and as I briefly just mentioned before, overlapping is not very good, because then it becomes less efficient to traverse the tree, less efficient to traverse the index, because, well, you don't know which branch you have to go to, and then you will end up having to go through both branches to see where this data point exists. Is it in the first branch or in the second branch, in the first cluster or in the second cluster? And in terms of the balance, the tree is balanced, so the children of the node, the degree of the node is usually bounded, so there is a minimum and an upper bound, and they're going to be plus or minus 1 the same, so it's balanced. And the objects or the data, actual data points, are only stored at the end, so only at the leaves. And all the nodes that are in the middle, they're just for navigation, just for routing, and they just hold the coordinates of the minimum bounding rectangle point, so when you are searching through the tree, you can actually understand which are you actually in this point of space or not. And the minimum bounding rectangles are used as the geometry. So this is what is used in R trees. The root has at least 2 children. So this is special rule. Of course, if you just have 1 child, so you might as well just delete the old root, and that new child becomes the new root. And for the number of children that you have, as I said, there's going to be a minimum or an upper bound, and these are defined by small m and big M. And I think you probably know now what the trick is going to be. So it's basically like what we did in the P-tree. How do we decide on them? What did we do in the B-trees? You're smiling. I know you know the answer. You already asked.
We fix the amps to the size of the block.
Exactly. So we fix the size of the amps to the size of the block. We have a minimum bound. So this is the lower bound. And the lower bound, according to a rule of thumb, should always be half the size of the upper bound. And the upper bound, like we said, should always be equal to the size of a block. So all the data points that are, all the children that are within the node, their data points, their size together should equate to a single disk block. And this then becomes more efficient because then you just go, you retrieve the disk block into main memory and you read it, and this then becomes faster. Good. Since our tree is balanced, so all the leaves will be on the same level. Maybe there's one level more, plus or minus one. And again, for the leaves, the number of children that they have, they still conform to the lower and upper bound. So they're going to be between M and M childs. The internal nodes, which were the data pages, these have I, and I is the smallest bounding rectangle. So these are the coordinates of the different minimum bounding rectangles that you have. So the geometrical region that is holding the data points. And it has the child pointers, so the pointers to the children that are within this cluster. And when you reach the leaf node, at the end, you have the smallest minimum bounding rectangle that is basically around the different data points. So this is the upper level. And then at the very end, you reach the leaf nodes. And then they have the smallest minimum bounding rectangle that is actually fragmented up to the maximum it can get. And at the end, the tuple ID. So you've actually reached the data point that you want, and you hop into the data warehouse or no, into the disks and get them. Cool? So this is how the R tree looks like, theoretically, or these are the characteristics of an R tree. And now we can start looking at the operations of the R tree. Any questions until now? Perhaps? Okay. Things might as well be more clear when we start looking at the operations. So, as we said, it's a dynamic tree. This means you can insert, update, and delete. So these are typical operations. Insert is one might also say the most important operation, and the efficiency of the tree, the efficiency of your index structure depends heavily on the insert operation, because at the end, both the updates and the delete operations, as we will see later on, at the end, the very end, they are converted somehow into an insert operation. So insert is very important. And then we have the search. For the data warehousing, we'll be doing that a lot. And the splitting operation, this is special. And this has to do with maintaining the tree, because we always have to make sure that the tree doesn't degenerate. We always want this bushiness. We want the levels to be nicely fitting to the underlying blocks. So we don't want trees that our branches are short or sites where the branches are long. We rather want to keep to the minimum and the lower and upper bounds, the small m and m. So we'll see that when we try to insert in a node higher than its capacity, which is the big M, then we need to split the node and kind of like readjust and organize the tree so that it conforms to these lower and upper bounds, and prevent this degeneration, which then makes our index not very, very efficient. Good. So the first operation is the searching in the R trees. Well, basically, the search is done recursively, and you start from the root, from the very top of the tree. And usually you don't know which branch you're going to start with, or to avoid the worst case scenario, what usually is done is you choose a path in the tree to go into, and to avoid the worst case scenario of finding the data point at the last branch, what we do is usually this is done arbitrarily, or you choose the path in a random fashion. And if you have the root here, and then you have different branches, and then you say arbitrary, I'm going to choose the first path, and then you follow it until you reach a point where you find out, okay, the search cannot be here, so you prune this side, then you go to this side, and so on. If you're lucky, you find it in the first branch. If you're unlucky, you will find it in the last branch that you look at, right? So to avoid this worst case scenario, you always do that randomly, which as the randomness has to do with which path to choose. So as an example here, we have our search query is here. So this is where it actually lies. And what we do, we start recursively from the top. So we go here with our search query, and at the top we check, is it in the root, is there any intersection with the root or not? And the root basically is this minimum bounding rectangle. So all of this over here, right? Seems feasible, so we start going down the tree. So assume the first tree that we needed randomly selected is the one on the left side, so R1. So we go here and we check if there is some kind of an intersection. And we'll see that there's no intersection at all. So then we prune. So this is the power now of the index. We say, okay, it cannot be here, so this branch is completely ignored. So now we start again and choose another path. And if you're unlucky, you choose this path, R3. You do the same thing. Is there an intersection between the query and R3? And you'll find that there's no intersection. So you prune this path as well. Now, only one option left. You go to R2, and you ask the same question, and you see, well, there is an intersection. So you start going down and checking the children. Again, this is done randomly. You check the different paths, and until the end, at the very end, you find R8. Now, in the worst case scenario, what we did here is we basically had to traverse 1, 2, 3, 4, 5, 6, 7. 7 nodes in the tree until we found R8, so until we found the answer to our query. If we did not have that, then you would have basically had to look in the root 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So as you can see, even if you're completely unlucky and you choose the worst branches that you go into, still the pruning effect is worthwhile. And by traversing the tree, by traversing this clever construction, you can then find quickly, relatively quickly, whether your search query is there or not from the very beginning. Cool? Good. Wait. Good. So you can already imagine when we talked about B trees at the very beginning, I told you it has a logarithmic cost. And this was easy to say because it was rather fixed. However, here in the R trees, as you've seen, you've heard me saying worst case scenario, and you pick the paths randomly. So as you can already tell now, you don't have a guarantee for a good performance because you never know. You might get the worst random choice, so you don't have this guarantee for a good performance. And as the worst case scenario, you might have to traverse all the different paths in the trees. And this might also be worse if you have an overlap. So an overlap here might be something like a point that is here. Okay, so imagine that our search query now is actually not here, but here, right? And now, when you start traversing the tree, you will go into the root, you go into R1, and R1 here will have, well, R4, R5, R6, and then R4 might also have different children, and so on and so forth. And at that point, when you reach this point of the tree, you can prune R5, but you can't prune R4 and R6, because you do not know which point, where is the search query. Is it an R4 or R6? So what you need to do, you have to traverse R4, and you have to traverse R6. You do not know where it is. So with overlapping, this makes things even worse. Good. So the power of using an index is this pruning ability. So as you've seen, as soon as you find yourself in a branch that will never contain your search query, you basically exclude this branch and you start looking, you stop looking at it, and you start exploring other paths in the index. And this is what basically allowed us to have this 7 searches, 7 traverses in the tree instead of having 12, because we pruned the first, the leftmost branch, and the rightmost branch. And this is basically what makes indexes very powerful. So how does the search procedure works? Well, at the very beginning, you start with the query, and the query is basically a search rectangle, and you start at the very beginning. So from the top, from the roots, and you start searching in the internal nodes, so the nodes that have the coordinates of the minimum bounding rectangle and the pointers to the children. And you check for the intersection with the query. And the intersection with the query, it's a very easy operation to do, because you basically need just to intersect the coordinates of the rectangle, right? So you can easily tell by comparing the coordinates if there's an intersection or if there's no intersection at all. Because remember, this is points in space, a Euclidean space, so you can say if this is bigger or smaller. So once the corner on the top is bigger than the corner here, then this means okay. Then I go to the other dimension, the x-axis, and check if it's actually on this side or inside. So this intersection, this calculation is rather easy to do. Good. And then if there is an intersection, then you start looking in the children. If there's no intersection, you prune the branch, and you're done with this path of the tree. Once you reach the leaf nodes, so you found a path that leads you to a leaf node where the data points are actually there, you start checking the data points themselves, and you start checking as well, do they intersect with the search query or not? And at the end, you take all the correct objects in the results set and return them to the user. So this is basically how it works. Everyone clear on the search operation, how it works? Problems when you have overlapping, this will be handled shortly. But as you've seen, this is basically going to be the most important operations that you're going to do with data warehousing. Next is also a very important operation in terms of the efficiency of the tree. And this is basically now the insertion. So when you want to insert a new node into the tree, what are the considerations, and what do you need to take into mind? Well, basically you have to find, of course, a leaf node that fits the point that you're trying to insert. So it has to be within the neighborhood, of course, of the point. And being in the neighborhood has to do with, well, how far the new point is to the current points that we have in space. And since you want to group the points closer to each other, since you have this notion of the minimum bounding rectangle, then this minimum bounding rectangle over here, and this one over here, and this one over here, you always want to include this point at the cluster where the rectangle will grow as small as possible to include this point. Because if you choose this cluster to include this new point over here, then you're creating a lot of dead space, so a lot of space that doesn't contain any points. And then you fall into the pitfall of when you get a search query, here you don't know if it actually exists or not, and then you have to traverse the tree and start looking in this branch when it actually doesn't exist. So the whole idea is group the points that are close to each other. If there's a new point, the minimum bounding rectangle has to grow, the volume of growth has to be as small as possible to include this new point. And this then decreases the probability that a search query will fall into dead space. The bigger the bounding rectangles are, the higher the probability that when you get a search query, it's going to be in a dead space, and then you have to traverse that path of the tree when you didn't need to. You could have only pruned it and moved on with it. So the key thing is you include it in the cluster, in the minimum bounding rectangle that moves as small as possible, that grows as small as possible to include this new object. So an example here, so this is nicer than the one I actually drew. You have a new point here, the x, and now you have to decide where to include it. As you can see, if you go R1, you have a lot of dead space. And the bigger the dead space you create in your root, you only have now this area over here that actually have this pruning power. So only if a search query comes in this blue part, you can say it does not exist and you prune the branches. But now all of this space over here, it doesn't give you this opportunity or this ability to prune. So you're basically wasting your time. A better thing to do is basically grow R2, because then the volume is smaller. Right? This is one thing to look at. So one of the criteria is the smallest volume growth. Another problem, or something that you need to also look at, is the overlapping. Now, as you can imagine, if the minimum bounding rectangle grows very big, not only is it with a higher probability that your search query will end up in that space, but now your bounding rectangles are big, and this also raises the chances that you're going to get overlaps. And overlaps, we don't like that, we hate that, because we don't know which path of the tree to traverse. So you cannot make a decision, and you have to go through both parts of the tree. So this is actually very bad, because here you're creating a lot of dead space, and moreover, you're creating overlap with R2 over here. So two things to keep in mind. You always want to create as less dead space as possible, and you always have to also minimize the overlapping that you do. Of course, minimizing overlapping, this is rather tricky. Unless you know pre-hand all the nodes that are going to be in your space, you can design the space quite elegantly without having overlaps. But once you start inserting records on the fly and dynamically, then sometimes it gets a bit tricky to basically maintain that. Good. So, as you can see, R1 produces a lot of unoccupied space, so dead space, very bad. If you're getting a search query in the dead space, a lot of traversing for nothing. And then the probability of a query then getting into that dead space is higher because you have a lot of it. So two things to keep into mind. Reduce dead space and reduce overlapping. So the perfect thing is if you have a minimum bounding rectangle like this, so R1 and R2, and you have points here and points here. And the new point that you're going to inserting is right in the middle. So this is perfect. It just fits directly into the cluster that you have. You don't need to grow anything, so no decision to do as to which cluster to contain in, because it's already within a cluster. Very good. If it falls somewhere outside, then you have to make the decision as in which cluster should you grow to include it, R1 or R2, right? The one with the smallest overall volume, so probably R1, only this volume over here, should be then chosen. Good? Good. So now that was basically the first thing that you need to keep in mind. You get a new point and you decide which cluster to put it in. Now that you've chosen the perfect cluster to put it in and you've enlarged the minimum volume rectangle, you still have one thing to consider, and this is there enough space or not? And this has to do with the upper and lower bands that we were talking about, and this has to do with keeping the tree from degenerating. And if there is still space and you still didn't reach the upper bound of 4 objects, 5 objects, whatever the number is, then you can easily insert the object within the leaf node and you're done with that. Good? If not, then you have to handle that. So if you now have the new point here and you decided that you're going to enlarge R1 to add it here, and these were the points that were already here, and let's say big M was 4. So as you can see here, you already have 1 point, 2 point, 3, 4. And adding this point, R1 now will be 5. And this doesn't work out. So what happens here is overflow handling. You have to handle this overflow. And what you do now is you basically now say, okay, we need to split this cluster into 2 because it cannot contain 5 points. And now the question is, how can you split it? Should you split it like that? And like this? Or maybe like this and this? So now comes the decision, how do you do the split? And as you can imagine, there are numerous ways to do the splits, right? So this becomes actually tricky and is rather difficult and non-trivial. So not only do you only have to do the splits within this cluster, but as you can imagine, this can actually cascade and go higher and higher. So if we had this one cluster and you decided to split it, and now it's 2 clusters, imagine the parent node had already 3 other clusters. So what you do now, you have to split the parent node. So this division actually can cascade right up until the root, because you're splitting at the bottom, the number of clusters increases, which increases the number of children for the parent above, and maybe the parent above also now is overflown, so you have to split the parent, and it goes up and up. So it becomes actually very difficult, and you have to maybe at some points reorganize the entire tree just from a split at the bottom. So you get this cascade event when the parents are also full, and if the grandparents are full, you also have to split the grandparents. And sometimes you have to even split the root, and you get 2 child nodes for the root, and then you get a new root. An example for that here to take a look at it and see this cascade effect is, let's see. So we have a new point to be inserted, which is xp over here, and our upper bound, the big M, is 3. So you're only allowed to have 3 points within a cluster. You're only allowed to have 3 children. Good? And now you've decided, well, we've already passed the first step of deciding which cluster to put it in. So it was clear that it has to be in R2. And the second step was, should it be in R7 or in R9 or in R8? And as you can imagine, the one who would grow the least to include this new point would be R7. If we had chosen R9, bigger volume, so dead space, and as well, which is very bad, overlapping with R7. So this is not the way to go. And R8 as well, very big, and overlap with R9 and R7, worse and worse. So this was an easy decision. We put it in R7, and R7, basically, for assumption's sake, it had already 3 points, and now by adding XP, it gets 4 children, so you get overflow. And now we need to decide about how to do the split. So assuming now that we have techniques that helps us in deciding how we split the clusters, and we know how to do that perfectly for now, we say, okay, we're going to split them. So we split R7 now. So this is the one here. And we split it into 2. Good? Very good. Problem now is R2, which is the minimum boundary rectangle. It used to have R7, R8, and R9, which is exactly 3 children. Problem is now it has 4 children. So what do? We have to split R2. So probably 2 children, R7, R8, goes with one node. And then R7b and R9 goes with another node. And so on and so forth. You'll see that the root as well, it already had R2, R1, R3, only 3 children. So now you also have to split the root into 2. And some has R1, R2, and another one has R3 and R4, for instance. Let's look at that in the next slide so that it's clearer. Good. So now what we did is R7 has been split into 2, R7, R7b. And R2, now since it has 4 children, we split it into R7 and R8. And then you have R2b. And R2b now has 2 children, R7b and R9. Now the root, the old root, it has to handle R1, R2, R2b, R3, overflow. What do? We have to divide it into 2. So we did a split. Horizontal split over here. And now we have a new internal node. So this is not called root A. It is not a root. It could have been R0 dash, for instance, and R0 double dashes. And this is an internal root, and now it holds 2 clusters only, R1 and R3. And a second internal node now holds R2 and R2b. And on top of these 2, we create a new root. So now we have the root. And the root now has root A and root B over here. And each one has the corresponding clusters. So root A has R1 and R3 now, and root B has the R2 and the R2b. See how the cascading effects work? We started with having to split R7, and then that went higher up into splitting R2, and that went higher up into splitting the root so that it can accommodate both R1, R2, R2b, and R3. So splitting, not trivial. Sometimes you have to go up right until the very top. Good. So we've assumed for now that we know how to do the splitting, so that you can see how it actually goes up the tree. But how do you actually choose the split? That is rather interesting and is a problem on its own, because there's going to be an exponential number of splits that you can do in space to get the different points, the overflowing points together. And an example here is, let's, for instance, assume we have these 4 clusters here, and they're overflowing, and we need to decide on a split. What you could do is you could, well, split these together. Of course, this has to be a rectangle, but it's easier for me to draw now. And as you can see now, this is a bad split. And why is that?
The minimal bounding rectangle is quite huge.
Exactly. So this generates dead space. So all of this is dead space. And if you get a search query and it hits here, a lot of traversing the tree for no reason. Good. So something that might be a little bit better would be something like that. So we group these 2 together and these 2 together. It's a little bit better than that one here, but still it's not perfect. Any idea? What is problematic with this one here? Overlapping, exactly. So we have always to keep into mind dead space and overlapping. And as you see from this example, it's very hard to find a perfect world when you will never have both dead space or overlapping. Is that mine? I do apologize for that if it's mine. Sorry about that. You will never find a perfect world when you will have no dead space or overlapping, but rather it's going to be a trade-off. You always have to find a balance, either dead space or overlapping. And as we'll see later on in the lecture, there are some techniques or some ways where you can handle overlapping a bit, but dead space, there's nothing you can do about it. So maybe having a little bit of overlap, you can handle it a little bit. Either you build the tree again, or you copy the values in both branches of the tree. We'll get to that. But for now, splitting or making the decision to split, you're going to have not only these 2 splits, but rather you're going to find a lot of different splits or variation of splits that you can do, and deciding on one becomes then a non-trivial and rather difficult and interesting problem. So the most naive thing to do, the simplest idea is, well, basically look at all the different possibilities that you can do. So we always talked about having a minimum bounding rectangle, right? So we always want to increase when you add a point or when you do the split, you want to have the smallest bounding rectangle. As soon as they're big, then you have that space. So what we do is we try all the different splits, and the split that yields the smallest possible MBR then is the winner. This is the split that we can do. If you consider all the different splits that you can do, this is going to be exponential. So the potency set of all the possible divisions that you can do in space, this is going to take a lot of time, and this is not doable. So this is naive approach. Can we do better? Of course. We have here 2 different techniques. One is quadratic cost, so better than a naive approach with this exponential cost. And we also have a better one with a linear cost. So doing this naive way of trying all the different splits is out of the question, and you should not do that. If you want to have a technique with a quadratic cost, well, what do? Well, first off, you think, well, you have the space and you have the different points. Now you need to decide on a split. So what you do at the very beginning is you check each 2 points together at the very beginning, and you check which one of them produces the biggest bounding rectangle. And that would be here these 2, probably. Right? And why is that? What is interesting about the 2 points that produces the biggest bounding rectangle? They are, sorry?
They are most likely to include some other points.
It would be the worst decision to put those two in one cluster.
Mm-hmm, exactly.
You want to know about them.
Yeah. So these 2 points, they're producing the biggest minimum bounding rectangle, which means they produce the biggest dead space. It's a bad idea to put them together. So from the very beginning, you basically look at the 2 extreme points of your space and you say, these 2, they're not going to work together. I'm going to separate them. And they're going to be the starting points of new minimum bounding rectangles, right? So you start here, and these are kind of like the seeds, if you want to call them. And they start the new minimum bounding rectangles. And once you've decided that, you then start to do the normal thing, or the thing that we've been doing in insertion. So you start checking, you look at each point, and you compare it to the 2 minimum bounding rectangles, and you see which one has to grow less to include that point. And here the winner is the first cluster. So you include this point in this cluster, and you go on and on like that with the different points in the space until you reach the split. But the beginning, you identify which 2 points should not be together in space. Very good. So you start up with the 2 objects that create the largest minimum bounding rectangle. And as soon as they found them, they become the starting points. So these are the 2 seeds, and they create 2 new minimum bounding rectangles. And then what you do now, for all the other objects, all the other data points in space, you start to compute the difference in the distance, and you compare which minimum bounding rectangle grows the less, so it has the minimum volume increase. And once you found that, you insert it into the corresponding minimum bounding rectangle that increased as less as possible. So the object is inserted in the smallest difference in the corresponding minimum bounding rectangle. And you repeat this procedure then for all the data points that hasn't been placed in a minimum bounding rectangle yet. Good? So this is better than the exponential, than the naive way, but still it has a quadratic cause. Can we do better? Well, looking at, we're working in a data space, and we're working with a Euclidean space. And the idea that came into mind is why not exploit that? So we have these nice axes, and you have the different clusters. And the idea is, well, why not look at these coordinates over here? And since the dimensions are ordered, since we're working in a Euclidean space, well, then it should be easy to compute the distances between the different clusters. And the idea is the one with the quadratic cause and the naive one, you had at the end to look at all the different individual points and do a comparison between them. And the idea with the linear cause is why not just look at the extreme points and just compute the distance between them instead of looking at everything that is in the middle. So how does that look like? Well, you look at, again, the 2 furthest points that are apart in the space. But we're working on axes, so in each dimension that you have now we're going to be looking at 2 dimensions, one on the x-axis, one on the y-axis, and we're going to be looking at highest minimum and smallest maximum. So if we have here the x-axis and the y-axis, the highest minimum will be, on the y-axis will be the minimum value will be the smallest value that you have, and highest meaning highest as in the upper corner of a cluster. That is minimum. So if we have 2 clusters on the x-axis, this would be the point that we're looking at. So this is the minimum on the x-axis. So this might be 3, and this might be a half. So this has the minimum, and you look at the highest point. So you choose that point. Okay? And if you're looking at the smallest maximum, this would be the maximum point on the x-axis. So this is the biggest one on the x-axis, this line over here. And the smallest would be that one here. Right? So this is just to understand what each coordinate means. And then what you do is, you look at these 2 points, and you look at the distance between them. And because we're working with different dimension and the different dimensions span differently, so on the x-axis you might have clusters that reach up to 10, whatever the centimeters or whatever you have, whatever measure you have on that axis, and on the y-axis or on the different other dimensions you might have different measures, so you have to always normalize them. So then by normalizing them you take the size of all the rectangles within this dimension, so that later on you can decide on which dimension you do the split. Good? And then the one with the highest normalized distance is the winner. So let's look closely at an example so we can basically imagine that. So we have here, as I said, only 2 dimensions here. So the x-axis and the y-axis. And now we start looking at these 2 coordinate points. So this, the highest minimum. So in the x direction, that would be the minimum here. So this is this cluster over here. It has the minimum. So it's bounded here. It's on the lower side, lower bound of the x-axis. And if you look on the other side of the x-axis, what is the maximum? Well, you have D over here, you have C over here, and E. So it's obviously E. So these are basically the 2 clusters that you should look at. And you check what is the distance between them. So what is actually the split? What are you going to gain if you split them apart? Well, if you split them apart, you're going to have, there's going to be a distance of 5 units between them. Good. If you look at the y-axis, so you want to decide if you do the split on the x-axis or on the y-axis. We do the same thing. So we start looking on this axis over here, and then the 2 clusters that we obviously need to look at. Here is the minimum. B is here, E is here, D, A. So this is the minimum. You take C. And then the maximum would be, you have B here, here, here. So D. So you look at D. And then again, you check what would you gain by the split. So 8. Bigger split. And of course, because we're in different dimensions, we normalize them so that we can actually compare the 2 distances together. And how we do that? Well, basically you divide them across the whole distance. So for the y direction, you get the difference between them, which is basically this here, 8. And you normalize it across the whole distance of all the different clusters within this dimension, which is 13. We do the same thing in the x. You get here between A and E, the difference between them is 5. And if you normalize them, this is the maximum across the x dimension, 14. And then you compare the 2 distances together, and the one, you see that dx will be smaller than dy, so you choose to do the split across the y dimension, and C and D are chosen then for the split. And now the cost becomes linear because all you needed to do is basically look at these coordinate points. And you didn't need to look at everything that is in between. So for the x dimension, you only looked at A and E, and you didn't have to check, well, what about D and B and C? That was irrelevant for me. In the y dimension, you also looked at C and D. So you only looked at 2 points and did just the calculation on it. So very clever and easier to do than the other costs. Of course, higher dimensions, you have to do it in the different dimensions then, and then at the end, compare between them. Everyone clear? Very good. Okay. So, well, we did basically the splitting to handle the overflow problem, right? And what we did there now is you have to do that iteratively. So you insert the remaining objects within a minimum bounding rectangle with the smallest volume growth. So as soon as you figured where you're going to do the split across which dimension, then you basically then insert the others like we did before, within the minimum bounding rectangle that is going to grow as least as possible. And it's basically here a simplification of the quadratic cos and the naive one, because you only now look at the coordinate points rather than everything that is in the middle. It doesn't produce the best split, however, it is sufficient. So you'll usually get minimal overlap, which is always a good thing and always something that is desirable and something that we want. Minimum overlap, smallest dead space as possible. Okay, so that was the insert operation, and as I've told you before, insert operation is rather very important because the delete and the update at the end turns into an insert operation. So the delete operation, basically in the insert we looked at the upper bound. If you're inserting a new object in the tree, you always had to make sure, well, the minimum bounding rectangle has to grow as small as possible. And once you found the perfect minimum bounding rectangle, a perfect neighborhood, then you had to check, well, can I actually put the object in there? Can I put the data point there, or is there going to be an overflow? With the delete, you're deleting an object. So you have to look at the lower bound. You have to see, well, when I throw this guy out, is it now too small? And then you have this, you're condensing the node. And once you do that, and now the lower bound, which is the small m, is, so you're below this threshold. So what you need to do now, well, you end up deleting this node because it's too small, and then you have to reinsert it in the tree. So the delete operation at the end is basically, you either have the perfect solution, the ideal situation where you delete the object, and the tree is still balanced, you're still conforming to the lower bound. If not, and you're below the threshold, then you delete that entire node with that extra, with the child that still should be there, and you reinsert it from the top. In a special case, if the root remains with just one child, then of course this child becomes the new root. So an example, let's assume here now that our lower bound is 2, so you should not have lesser than 2 children. And R9 here had basically 2 childs here. And now we're going to delete this guy over here. So we go into R9 and we remove this data point. And what happens is R9 now has only 1 child that is here. And this is lower than the lower bound that we have. So what do we do now? We delete R9, and we take this point, and we do this insertion operation. So everything that we've been talking about so far. You try to insert it, you find the minimum rectangle that grows the less, and then you check, is there an overflow or not? Do I need to do a split? And so on and so forth. So here you take the point, and then you see which minimum bounding rectangle should I take it in. R8 would grow this much. This seems the most reasonable solution. If you use R7, doesn't sound very good, because then you have to overlap with R8, which is bad, not good. So you choose R8, and we're assuming here that R8 had already only one child, but probably not, because if it had only 1 child, then it would have also been deleted. So you probably have to split and go up the tree as you insert this new object. Everyone clear on that? So it basically goes back to the insert operation, unless it's the ideal situation, and m, for instance, was 3 here. So, well, no, actually m was 1 here. Then deleting this object wouldn't have been a problem, and then the tree would have stayed the same. Good. Update operation. What do you do with the update? Well, the update is basically you're changing something in the tree, and if the change that you're going to do will leave the point in the exact minimum bounding rectangle that it was before, no problem. So you just change it, and it has more or less the same characteristics, and it's a different dimension, so it remains in the neighborhood. So maybe it goes here or something. However, if it changes completely, so it was a wrong entry, so probably it's going to be in a new neighborhood. So what do you do? So now it's somewhere outside. What are you going to do? You delete it, and you reinsert it. So we're back to the delete operation, and we're back to the insert operation. So the different operations are basically an insert in disguise, if you want to say it like that. So if we start looking now at, well, what is actually the cost depending on? The efficiency of the tree depends on, well, the cost of accessing the blocks. And you can surely know by now that there are two big factors here, which are the overlap and the dead space. And these are the ones that cause problem, and these are the ones that make you traverse the tree. If it's dead space, you're traversing the tree for nothing. If you have overlapping, then you're traversing the tree to know which branch you should end up in. So having a search query here, S, as you can see, lies in both clusters, so cluster B and cluster A. So at the end, if you're searching for it, you have to go through the root, you have to go through A, and you have to go through B, because you do not know where it is. It's actually here. And overlapping, there's no way to avoid it actually, unless you don't have any inserts, or your data is rather stable. So from the very beginning, you design your space and you build the index, and it stays as it is. But as it keeps evolving, overlapping or avoiding is rather difficult. And this is the main drawbacks of R trees. And there are different variations or improvements of R trees that allows you to handle that more efficiently, or in a better way, and that is the R plus trees. And the R plus trees have a very simple rule. So it prohibits the overlapping of the neighboring minimum bounding rectangles. And how does it do that? Well, if you have an object that is in both cluster A and B, and what you do in the root, you have A and B, and you have the children here, and you have the children here. That looks ugly. And basically, you put it in both branches. So you duplicate. Drawbacks of that, you need more storage, of course. If you update the tree, you have to make sure that you're updating in all the different branches. However, in the data warehouse, this is not often the case. So we usually don't do a lot of updates in the data warehouse. So it works. It's up to you, and you have to decide whether you want to do that, or it doesn't, or you can wait a little bit more and traverse different paths of the tree to find it. So an example here is, now you have S, and as you can see now, there's an overlap. It's in both P and cluster A as well. So what do we do here? We put G in both. So now if you get the search query coming here in the middle, you can only traverse A and find it, and that's going to be it. You don't have to traverse B anymore, because you are definitely 100% sure that you are going to find the answer to your query in either branches. So you don't now have to traverse and fall onto this worst case scenario that might happen, that you traverse the first branch and the data entry is not there. So this is how the R plus tree basically handles that. Performance, well, R plus tree definitely improved the search performance because now you don't have to traverse both sides of the tree, but rather one side of the tree. And if you have point queries, well, this basically saves up to 50%, so only one branch instead of two. And the drawback is, well, it degenerates quite quickly because you have, as soon as you start doing all of these splits, then you have to make sure that the tree is kept balanced. And then usually what you have to do is every once in a while you have to rebuild the trees. But scalability is similar to R trees. There are other trees that have other characteristics or handle the dead space and the overlapping trade-off better. So this is in the R star tree, so it has a clever algorithm to do basically the overlap and the dead space. It kind of like try to cleverly figure out the overlap, the trade-off between that. And there's also the extended nodes in the X tree. So these are special nodes which holds the data. And then the tree can figure out cleverly when the query comes in, if it is big and you have to traverse a lot in the tree. So it basically directs you directly to sequential scan. So it basically tells you when you should use the index and when you do not need to use the index. They're both, all of these trees are scalable up to 20 dimensions. If you want more information about that, we're going to be uploading the papers on the website, and you can have a look at that. So we basically presented the R trees to give you a good foundation, because all of these are basically extensions to that. Good. So this brings us to the first detour of today, and since I'm already here, so I'm just going to be doing it. However, I think you guys ought to have a break, right? So we'll be starting with the detour, so it's still a little bit of a breather before we head into the bitmap indices. So just sit back, relax, and in the detour I'll just be presenting another idea of extending B trees, because as we've seen in the first part of the lecture, we were talking about B trees, and it's perfect for indexing unidimensional data, where we had these branches. Left side was everything that is smaller, and everything that was bigger than a certain number or string, and so these were perfect. And the question was, well, can we do something with the B tree to make it multidimensional? And the question is, yes, we can. And the idea was basically, we want to take the multidimensional data and somehow do a kind of a transformation on the data. So in the last lecture we saw, when we had the product and the time dimension, we took it as arrays and we linearized it, and then we had these sequential reads, which was good in one dimension, and the other dimension didn't work very well when the query came on the dimension that was not linearized. And the idea is, can we do that without losing information and with the same concept? And this is where universal B trees comes in, and they're basically a combination of B star trees and Z curves. And the idea is, well, the problem with the linearization is that it gives us excellent access on one dimension, so we had these linear scans over here. But usually when you're asking a question, usually you need a block of data. So you need all the products that were sold in February and March, or you need different products. So we always have this kind of like, well, the same concept that was in the R trees, this concept or notion of data closeness, of neighborhood. So you typically want blocks of data. So the idea of UB trees is, well, why not linearize the data in blocks, in small blocks like that? And then when we read them, each block of data that seems close to each other, similar to each other, such data would be then, this closeness or similarity should be mapped as well on disks, and then these should be linearized because they seem to be close together, and they would be then queried together. And So what the UB trees do, they take the data, they linearize them in this neighborhood fashion, and once they do this linearization, these blocks, in order to access the data on disk then, during this transformation they produce Z values, and the Z values basically gives you the coordinates of the different blocks, because you have different blocks now of your data, and then you need some coordinates to know, okay, which is the next block, how to jump from one block to the next, and we'll see that in the next slide directly. But this is the basic idea. So if this is our, following the example that we had from last lecture, the time and the product dimension, and instead of going linearly like this, which would be perfect in one dimension, we want now this kind of like neighborhood effect. So what we do is basically you start grouping data together. So you take the multi-dimensional data and now you want to linearize it in a neighborhood fashion. So what we do now is we group them together like this. So basically you read and then you hop here, you read, then you hop here, you read, you hop, you read, and so on. And now you see these Z curves. You read, you hop, you read, you hop, you read, you hop, and you have these Z curves, and that's why it's called Z curves. And if you look at the coordinates here, so these are the Z values that come 1, 2, 3, 4, 5, 6, 7, 8, 9. Each colored region is called a Z region, and this basically constitutes one disk block. So then you have, this is one disk block, this is one disk block plus this one here, and the orange as well is another disk block, and so on and so forth. So now you're basically dividing the data with blocks, and this is what the UB or the Z curve, this function that Z curves use, does. The problem is now, or not the problem is, well, now since we've done that, we need to know how to actually go around in this linearized data. So how do I actually get from one point to the other, from one block to the other? You get these Z values as soon as you cluster the data together. But these are actually very easy to compute and very efficient to compute because it's based on bits. So what we do is, well, if you want to find the coordinate of a certain cell, you basically look at the axes. So the coordinates of the axis of the X and the Y. So for instance here, to follow the example that we already have in the slides, to know where this cell lies in the space. This is the Z value, so this is 51. You want to know where does it actually lie. Well then, you can go either way. So the transformation is two ways. You take the 51, and you represent it, of course you negate the offset because you start here, if you're talking about bits, you start from 0, so you take -1, the offset, and then you get 50, and you represent the 50 in the binary representation. And then what basically you do then, it's kind of a little bit of a trick. This 50 binary representation, if you start splitting them, you take the first one, and the third one, and the fourth one, you get this value, and then you take the second, the fourth, and the sixth, and you get this value, and these are basically then the coordinates that you have. So this is basically 5, which is the y-axis here, and x4, which is the x-axis here. If you'd started with the coordinates, and you want to find the value, which is exactly then the same, you take the x-axis, which is 4, you turn it into the bit representation, and you take the y-axis, which is 5, you turn in the bit representation, and you start then interleaving them. So this goes here, 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 and this one goes here, here, and here. And this basically allows you to kind of like find your place within the space, as how you basically created it with the Z curves. And The different colors are called Z regions, and usually you know how many nodes you have within the region. So here we have 9. So you have a region from 1 to 9, 10 to 18, 19 to 28. So when your search query comes, you need to know where it lies in the space. So you do this bit interleaving, and then you figure out which block to get. And this has to do with the Z region. So you locate the Z region, and then you can start retrieving the block and finding the query that you want. An example for the searching then would be, well, you get a query, and the query basically is specified by 2 coordinates. And the coordinates is basically, if you say this is the query, then the coordinate is given by the upper left corner and the lower right corner. So you compute the upper left corner. So this is done by the interleaving, and then as soon as you find out that you're actually at coordinate number 15, so this is the Z value 15, then you check what are the regions that I have, what are the Z regions that I have, and it was basically 1 to 9. So this is 15 is bigger than 1 to 9, and the second Z region that we had was 10 to 18. So we retrieve then, this is the disk block, or this is the Z region that you need. And you then retrieve the corresponding page and you load it in. And this is basically the green one here. So this is the first disk block that you got over here. And as you see, the query only needs 15 and 16. So you start looking in the page and you'll find out that, well, you wanted 15, and 15 basically on the axis is x equal 3 and y equal 4. So 10x is basically equal 1. These are the coordinates. So you do the interleaving process, and you're going to find that, okay, 15 is bigger, so you skip all that until you reach this point, and then you can read sequentially, right? And again, you reach at 1.17 because you're reading sequentially, and you'll find out that, okay, this is not the next one that I wanted. It's actually 27. And these are called then the jumps, the Z jumps, and you need then to compute. So every time you need to compute the coordinates as soon as you hit a new block, and then you have to find the Z region that you want, and you load that, and you find out at the end of the query block from this right corner down over here, 58. And if you look now, how many disk blocks you retrieve? Well, they're basically 1, 2, 3, 4, and 5. So you need 5 to load 5 pages in memory. But this is probably better than had you done it linearly, because then you have to read sequentially, and this might be very big. So a lot of wasted data. But here you try to kind of localize the data that you're reading through this notion of neighborhood. And the critical point, of course, is computing these jump points, so the coordinates within the regions, and these are rather efficient because they're basically at the end just bit interleaving, so they're not very hard to do or very slow. However, if they take too long, so this would be the bottleneck in such an algorithm, but to do these operations you just need the 2 coordinates of the search query, the upper left and the lower right coordinate, and the current Z value, and then you should be able to do the computation. And of course there are different other, so these are Z curves, there are piano curves, there's a lot of different functions that are out there that allows you to do some kind of multi-dimensional linearization, but kind of like in blocks and neighborhoods rather than just linearization. Z curves are basically very good for range queries. So queries that are between spans or between a range of products in a lexical order, and the similarity is basically done by neighborhood. So you just don't linearize in one dimension and say that's it, but rather you try to take the different dimensions into consideration and measure the similarity of objects within the data space and kind of like group them together. And this is basically the idea of the Z curves. And you usually have a high node fill-in degree, so it's rather a dense space, and in terms of complexity, it's rather logarithmic. So this was just an idea or another kinds of trees that we wanted to basically just give you an idea about. Good. So the last types of index that we're going to talk about today is actually very simple, and sometimes simple is the best thing that you can do. And these are bitmaps indexes, and they were specifically designed for data warehousing. So our trees, these were, as you've noticed at the very beginning, I said they were done back then for geoinformation system. There's a lot of emphasis on balancing the tree, on the insert, delete, and update operation, which is actually doesn't happen that often in the data warehouse. So data warehousing, usually it's going to remain fixed. You're going to do a lot of search. So updating is not really our focus. So there's no need to look at that extensively, but rather you want to build a data structure that is more oriented to service the querying aspect, that you're going to read the data. So the idea was, well, we use bitmaps. And what are bitmaps? Well, bitmaps are basically arrays, and arrays are made up of bits. So you have ones and zeros and yeah, exactly. So you create bitmaps for dimensions. So looking back at how we had the data warehouse, we had the fact table, and then we had the different dimensions. And the problem or the bottleneck was, well, you had to go through the fact table and then follow the foreign keys into the dimensions, right? And whenever you had a query, you had to do all the different joins, which was bad. And then you have to follow them and get the data. The idea here now is, well, instead of doing the joining, why not use or exploit the fact that our hardware is very good at logical operations, at working with bits. This is basically the most efficient operation that you can do on your computer. Since we're going to do a lot of, we're wasting a lot of time with getting the data and working with actual data, and joining the data is actually taking a lot of time and consuming a lot of time. If we can convert the data into bits and just work with bits and logical ands and ors, it can actually make our search or queries performance very fast. And this is the whole idea. So how can we actually do that? Well, as a rule of thumb, bitmap indexes work best with dimensions or these granularities that have a small set of distinct values. So something like the gender, where it has only female or male, or something like if you don't have a lot of different stores, so you just have a store in Braunschweig, in Hannover, in Göttingen, so just a distinct number of values. Then what you can do is, for every distinct value, you create a bitmap. And then the bitmap, basically, you have here, let's say, the fact table. And the fact table, these were usually foreign keys, so let's say the table is now joined. So you create a bitmap for every distinct value, for every different granularity within the dimension. And you say, if we take the bitmap for the female, you look in the fact table. In the first row, the employer, the customer was a female, you put a 1. In the second row, the customer was a male, it's a 0. The third row, male, 0, unspecified, still not a female. Fifth row, it's a female. And you create a bitmap for every distinct value that you have for the different dimensions. So how does that look like here? So here we had the fact table, and the fact table is basically sales for the different shops that you have. And so this is the measure in the fact table, the sum of the sales, and you have the different shop IDs. So this is the location dimension, and you only have here a small set of shops. So you don't have a lot of distinct values. You only have Saturn, Real, and Peek and Kloppenberg. So what you do now, you build a bitmap index. So a bitmap index is basically a group of bitmaps, vectors, and for each distinct value in the dimension table, you build a bitmap vector. So the size of the bitmap index basically is equal to the size of the distinct values in the dimension. So the bitmap index now has 3 bitmap vectors. one for Piken-Kloppenberg, one for Real, and one for Saturn. The length of the bitmap will be equal to the cardinality or to the number of tuples in the fact table. And instantly now you're thinking, the fact table is usually huge. And now you're telling me I need to create a bitmap vector for every single granularity for all the dimensions, and that the length is going to be the length of the cardinality of the fact table. Doesn't seem very good in terms of storage efficiency. And then you need to work on these bitmap vectors and do some kind of logical and or operation. Well, think about it. If the fact table has 1,000 tuple, what does that mean? It means that every bitmap vector has 1,000 bit. This is less than 1 kilobyte, isn't it? And working with 1 kilobyte, doing logical ands or ors, or working with them to get some answer, as we will see later, this can be done extremely fast. This is the best. This is what our computer is best at, doing these logical ands and or operations and working with bits. So this is basically the structure that we do now. And you have the bitmap index, and it has a collection of bit vectors. The bit vectors, the number of bit vectors that you have will be equal to the number of distinct values. So these was basically the 3 shops, Real, Piken-Kloppenberg, and Saturn. For each of these vectors, so Real, for instance, the length will be equal to the length of the fact table. So this means every time you add a new tuple in the fact table, you have to update the bit vectors, which means you add a bit at the end of each of these bit vectors. And usually what you do is you add a permanent number for each bit vector. So Real has been given the key 1. It should always remain in your data warehouse with the number 1. And Saturn was 2, so it should always be 2. This makes life a little bit easier. Good. And then, of course, you do a mapping. So this basically, which was before the foreign key, primary key relationship, so the joining, these numbers act like that. So what can we do actually with these bitmap vectors? Well, we'll come back to that in a minute, but looking at the size of the bitmap vector, well, if you have n records in the table, so n tuples in the fact table, and you have a distinct value, so this was in the location table 3 shops, so you had 3 shops, and then let's assume 1,000 tuple in the fact table, then the size of the bitmap index is basically the multiplication of both of these. So how many tuples multiplied by the distinct values, right? And what is really good or very efficient about bit vectors and bitmap indexes, I already said, of course, 1,000 bitmap vector, the size is very small. We're talking about kilobytes. But even then, what you will notice most of the time is, well, if you have only 3 shops, like the example before, this means that the probability of a product being sold in one of these shops, well, it's going to be high because there's only 3 shops. If the M is rather big, so you have, I don't know, you're Walmart or something, so you have a lot of branches, or you're an international company, and you have branches all over the world, Apple Store or something, then the probability that the product that is being sold in the fact table, being the one that is from the shop in Hamburg, will be not very big, which means that the bitmap index that you have, the bitmap index with all the bitmap vectors that are inside, for the one in Hamburg, for the Apple Store, there's going to be a lot of zeros. Every once in a while there's going to be a sales, a lot of zeros, and there's a 1. And this is going to be the same in all the different bitmap vectors that you have in the bitmap index. And this, of course, as soon as we see a lot of zeros, then this is an opportunity to compress, because you have a lot of zeros, so you can do easily compression. So this is very efficient in terms of actually storage. You can compress that using run length encoding. Very popular methods is a gzip, and especially for data warehousing, there's byte-aligned bitmap compression and variable byte length encoding, and this is basically from Oracle. Good. So what can we do actually once we've created all of these bitmap indexes and vectors? Well, assume now we're going to look at a different operation so that at the very end you see what you do when you get a search query and how fast you can actually do this, what used to be a join operation. So first off, let's start with a deletion operation. So this is basically your fact table, and you have the measures here, the sum, and then you have the shops here, right? And if you've decided that you're going to delete Zatron here, what happens? Well, remember this was the dimension table from before, and what we did was, so this was the bitmap index from before, and what we had was one bitmap vector for Peek and Kloppenberg, one for Real, one for Zatron, and these were basically what? Let's look at one of them. So Peek and Kloppenberg, the sales here, no, it's Zatron, it's from Real. Yes, it was from our shop. It was from Real, it was from Zatron, it was from Real. And this is exactly the representation that is here. 001 000 001 000. So this says there was in the fact table when you're looking for sales for Peek and Kloppenberg. The only thing that you need to do now, you look at the bit vector. And now, if that query came, I want to know the sum of the sales, all you need to do now is, you know exactly what you need to do. You just go to the fact table to tuple number 1, 2, 3, here, and you get the sum. Very quickly. You just need to look at the bitmap vector. Good. So with the deletion now, you deleted something from Zatron, right? So this is the fifth tuple. You don't have Zatron anymore, so what do? Well, you have two alternatives. Either you remove the fifth tuple and then you kind of like cascade that, so the sixth tuple becomes the fifth, and so on and so forth. However, we choose not to do that, so what we do is basically create a so-called tombstone here, and no one gets the fifth tuple anymore. And this allows us not to do a lot of updates in the bitmap vectors and the bitmap index. And the only thing we need to do is we go to all of our bitmap, not all of them, will actually only Real, Zatron. We go here and we say, okay, the fifth one, it's no longer for Zatron, and we change it from 1 to 0. Had you cascaded everything here, then what would you have needed to do? Well, basically, if you had chosen to completely delete this record from the database, from the fact table, then the fact table's length is no longer n, it is n minus 1. So the length of each of the bitmap vectors now has to be not n, but n minus 1. So you would have to have deleted all of these here, and the size then is smaller. So you'd have to go in each of the dimension and delete all the fifth entry. This is one solution. Another one, keep them, but just put a 0 in the dimension bitmap vector, and in the fact table just put a tombstone here, so this is not readable anymore, or you don't consider it anymore when you're doing when you want to answer a query about that. And anyway, it's not reachable anymore through the bitmap vectors, because if you look at the sum of the sales from Zatron here, you only have from the bitmap vector 1 in the first tuple, which is here, and this is exactly the tuple that you're going to retrieve, the first one, and that's it. It's no longer there. It's no longer in our records, even though it is saved. Okay, what about inserting? Well, inserting is actually not problematic, because what we do in the fact table, we always append. So new tuples always get inserted at the end. We don't insert in the middle. So that means it's very easy for us to update also the bitmap index, because what we need to do is we need to append a bit at the end. You have two alternatives. If here it was, let's assume for now, this was Real, right? So this is our original bitmap index. We had only 3 shops here, Peek and Kloppenberg, Real, and Zatron. So what we need to do now assume for now this didn't happen. Well, we added a new tuple, so, and this was real, right? So in real here now, we add at the end a 1, which means there was a sale from real. For Peek and Kloppenberg, this sale was not from their side, neither what is from Saturn. So you always have to add a bit at the end, because this basically represents the sale, so the cardinality has to be the same. If, however, you're inserting something new, so this might happen, you're inserting now Rewe, which is a new granularity that you did not have before, well, it's also quite easy. Then you add a new granularity here, this is Rewe, and then what you do, it never had a sale before because this is someone new, so the first 6 bits are zeros, and only the last sale now is 1, and of course, all the other granularities, Peek and Kloppenberg, Real, and Saturn, they get a 0 at the end because the sales was not from their side. Clear to everyone what we're trying to do here? It's quite easy, just playing with bits and representing the fact table with bits, so that we can easily then know which tuple to select very quickly from the fact table. Okay, updates. Again, here this was before Real, and we updated it to Rewe. So what we do now is, it is no longer from Real, so it's no longer a 1. We update it to 0, so the sales was now from Rewe. And assuming now it was a completely new store, we appended at the end, and it gets the sales at the second tuple. So here. Easy, isn't it? And here then is the beauty of the design. Actually, when you get a query, what do? You want the sales that are from Saturn and Peek and Kloppenberg. So all you need to do now, you need to get these 2 bit vectors, and you do an OR, which is very easy. And then with the resulting bit vector, you know exactly now where you need to go and select from the fact table. So you know you need to go to the first tuple, the third, and the fifth, and then you just do the summation and return the value to the user. So very easy, especially when the selectivity is high, which means then that you have a lot of restrictions on your query, so you're not returning a lot of tuples. And this actually is very fast, so you're storing a lot of bitmap vectors, however they are in bits, and you can also do compression, you can always compress them. So it's a trade-off between both, but the computations then and the performance, it's extremely fast to answer queries in this method. So very efficient, very easy to implement. I mean, it's hardware supported. However, for each new value of an attribute, so if you have more shops, like for instance Rewe, you have to introduce a new bitmap vector. So as soon as we had Rewe, we had to create a new bitmap vector. And remember at the very beginning we said, okay, these are actually good if you have a small set of distinct values, only 3 shops, 4 shops. But if you're creating a bitmap vector for something like the day, well, you have 365 days in a year. And divided by 8 bits, you get something like 46 bytes for a record. How can we handle that? We can do multi-component bitmaps. We'll look at that. Another thing that you might consider might be a little bit problematic could be range queries. And range queries are basically spanning across different months. So what were the sales from March until June or something? How can you do that now with a bitmap vector? You can't just easily do it with just, well, then you have to read a lot of bitmap vectors and do the ands, for instance, or ors. Is there a better way to do that? Yes. It's called range encoded bitmap indexes. So let's take a look at both of them. Very easy ideas. So first off was the problem of having a large number of distinct values. So you want to create a bitmap vector for the number of the days that you have, or for this example, for the months. So you have 12 distinct values, so you have 12 months. What you can do is you create a bitmap index of size 12, which means you have 12 bitmap vectors. And whenever you want to do an operation, you just pick the bitmap vectors that you want. Can you be more efficient in terms of storage? Well, you can do that with a little bit of a mathematical trick. And what you do is you say, okay, I'm actually going to represent the number. So we have now 12 months, and the values is now from 0 to 11. And what we can do is then we can represent each vector by the help of two separate values. So we divide the month into two components with a function. And we say we can replicate or reproduce that number by using such a formula. So month December, for instance, is basically would be 4 multiplied by 3 plus 4. You get a 12. And as soon as you find a function that actually can produce all the numbers that you need, the 365 days or the 12th month, and you know then the ranges of the different components, so the y and the z, what you can do now is instead of representing or having a bitmap index of 12 bitmap vectors, what you can do now is represent them only, well in this case by only 1, 2, 3, 4, 5, 6, 7 with 7 bitmap vectors. And how do you do that basically? Well, for month 5, so for June, what you can do is you follow the mathematical function that you have here, and you say, you look here and you say this is the y bitmap vector, and to get the 5th month it's basically in the first cell. If you put a 1 here, which means the value of y is 1, and for z 0, 1, 2, 3 the value is 1, so you put 1 and the years are 0. 4 multiply 1 is 4, and z is 1 plus 1 and 5, and you get the value 5. So instead of putting the 5 directly there, you just cleverly devise some function that divides the value into two components, and you use these two components then to build up the final value. So it's a trick to basically decompress the size that you have by just doing the computation on the fly, because the computations are never a bottleneck. It's very quick to do. You just look at the values and then substitute in the function that you have. So it's very fast to do. You just have to come up with the corresponding function and the different ranges that you have. So these are here. Okay? Good. An example would be to see how actually advantageous it is to use such a multi-component bitmap is, well, assume you have 100 days to index, so this would be, the index would be from 0 to 99. And then what you can do is basically divide them into two components, and each component would be a size of 10. So you reduce the storage up to 80%. Instead of having a bitmap index of 100 bitmap vectors, you can only have 20 bitmap vectors, which is basically 1 for the first component and 1 for the second component. And as soon as you combine these components together and just substitute the values in each component in the function that you have, you can replicate the 100 values. Good. Of course, then what only you need to do is you need to read the two vectors, so you have the two read operations instead of just one, because now you don't have the 100 bitmap vectors, but you have less, so you have only 20, and then you have to do two reads. But you save a lot in terms of storage. Good. The final thing that I'm going to talk about today, and it's very fast, is range encoded bitmap indexes, which was the problem, the second problem, or the issue that we had is what about range operations between March and August? And if you want to know the sales between March and August, then what we would usually have done is, well, basically, we would have retrieved this bitmap vector, all of these bitmap vectors, so 6 of them, and then we would do some kind of a logical operation between them, so an and get the sales between them. The idea is, well, what we can do is, as soon as a product has been sold in March, and there is a 1 here, from now on, it will always have been sold. So it's always a 1. And this then allows you to basically start looking at, if you want to know all the sales that happened after March, then you only need to look at the sales that didn't happen in February. So you take the bit vector in February, so the negation, everything that did not happen in February but happened in March, and that will be it. Let's look at that. So persons born between March and August. So as you see here, this person was born in January, and he is born for the end of time. A person here was born in April. He was not born in March or February or March. As soon as he's born, he remains born. And this, now, if you want to do persons born between March and August, instead of getting all of these vectors and adding them together, what you need to do now is, well, you just take February, everyone who was not born in February, but was born in August. Because now, everyone that was born in March is still born in August, right? Everyone was born in April is born in August. So you basically now, you have, let's take a look. This one, this record over here is a good one. He was not born in February, born in June, so this is right. This guy, not born in February, born in April, within the range. This guy was born in February, so this one doesn't work. So the leading one here came from January. So the negation here, it gives you 0, so it doesn't work. This guy was not born in February, however, he was born in April. Not born in February, not born at all yet, born later on. So just by looking at the negation of February and ending this vector, you get the answer that you wanted without actually having to look at the 6-bit vectors. It's just a simple logical operation, and you just exploit the fact that you replicate the value as soon as it happens. So once they were born in March, you put 1s in every other coming bitmap vector. If the query is limited only to one side, so everyone who's born after March, you just need to look at all the people who were not born in February, and that's it. If it's something limited like we had between March and August, then you have to look at those who were not born in February in A1, but were born in August. And you just take the 2 bitmap vectors and you do the logical operation. Good. Advantages, very great for indexing the dimensions, and it can be several times larger. However, it's very fast, these operations to do, and they're very good for ad hoc queries, and of course, because it's supported by the CPU unit, you can easily, very fast, get the answers to the query. Good, so I'm a little bit over my time. Hope I did not bore you. What we did today is we looked at B trees, and it's perfect for 1 dimensions. However, for multi-dimensional, doesn't really scale. You can do UB trees, piano trees, the curves. However, what we looked at most deeply is R trees. For R trees, we use minimum bounding rectangle as the geometrical region. So instead of looking at individual points, we started looking at clustering. Then we looked at the different operations that you can do. We looked at the overflow problem and how to handle the trade-off between dead space and overlapping. Other variations could have been R plus tree or R star trees. And then we started looking at bitmap indices, which were basically created for data warehousing. So this is a lot of playing with bits and logical operations, very easy and very simple, but sometimes the simplest things work the best. Good. Any questions, perhaps, for today? No? Okay, so next lecture we'll be talking about optimization. We'll look at partitioning, joins, and materialized views. And no questions, so I'll just leave you then for today. Thank you for the attention.